Okay, we begin here. We are going to discuss the precise definition of the limit today. And let's just get started with a very, very basic scenario. So we're going to start out easy. It's going to get difficult, and we'll go from there. Really, we want to look at this example. The limit as x approaches 3 of 2x minus 1 is equal to 5. After you took your test, would everybody agree that that limit is equal to 5? Yes. All I have to do is take the value that x is approaching and do what with it? Plug it in. 2 times 3 is 6, minus 1 is 5. That's easy to do, right? What if I were to graph this 2x minus 1, what does it look like? It's a line. Are there any gaps in it? No. And so it would be pretty easy to, just look at it and say, well, obviously, it's going to be 5. In mathematics, we never assume that we can say things like that. It's never, well, obviously, it's just going to be. We have to have a way to prove it. We've looked at limits in a very, very informal way. Now we have to view them as a very precise definition. This will be the hardest part of your next few days. In fact, for some of you, this will be the hardest part of the year. So this, I would say, is basically the most challenging material that we'll cover, I believe. I think that if you can wrap your brain around this, you'll be good to go for the rest of the year. So try to understand this with me. It says our current definition of a limit uses phrases like as x approaches and f of x gets closer to the limit. And the question is, why are these phrases problematic? We use these type of words. Anybody see a problem with that? And we say as x gets closer to 3, the function gets closer to 5. And then we actually plugged in values, didn't we? We could plug in a value, right? What's a value close to 3 that you could plug in? 2.9. What else should I plug in? When is it close enough? I mean, if I plug in 2.9, we all know that you could plug in 2.99. And you could plug in 2.999. You have an infinite number of x values that you could plug in between 0.29 or 2.999 and 3. So the reason why this is problematic is this. When are we close enough? When are we truly close enough to say, you know what, it's definitely going to be at 5? You guys remember the barcode function, right? And it looks like that's pretty much going to head towards, I don't know, 1 or 0 or something like that. And all of a sudden, as you get towards 0, it starts exploding up and down, right? So how do we know things like that don't happen right around where the limit is going to be? I mean, until we truly try an infinite number of points, how are you going to know for sure that something wonky doesn't happen? You guys like that wonky? So let's consider this function. F of x equals 2x minus 1 for x not equal to 3. But when x is equal to 3, we'll say that the function value is equal to 4. Let's consider that function. Okay? So let's graph this line, 2x minus 1. What's the y-intercept? -1. So I plot that. Slope is... So I go up 2 and over 1, up 2 and over 1, up 2 and over 1. Oh, but at 3, it's not equal to the function at 3, so I have a hole right there. At 3, what is the function actually equal to? 4. So as you can see, I have this type of shape here. This is what's going on. What up? So that's what our function looks like. Okay? Let's try to understand what's going on here. If we want to talk about the limit in this scenario, I want to talk about those values that are very, very, very close to that open circle, right? I mean, if we're talking about the limit, I kind of want to zoom in on this spot right here, right? And I would want to keep zooming in further and further and further to ensure that my y values are getting very, very close to 5. Well, let's think about the problem in a slightly different way. Let's consider this question. How close would you have to get to x equals 3 in order to ensure that you are within 0.01 of the limit 5? Please draw this. This is super important that you get this piece. If I'm within 0.01 of 5, what is the highest value I could be? If I'm within 0.01 of 5, what's the highest value I could be? 5.01. Very good. What is the smallest value I could be? 4.99. Excellent. If you got that, you made the first step. Yep. No, that's fine. Well, this graph says that the function is 2x minus 1, which is this line, but it says there's not an x value at 3 for that function. Instead, I have to use the value 4, which is up 1, 2, 3, 4. So this dot just makes sure that it's evaluated for every spot. Now, here's what the question is asking. It says, how close would you have to get to x? Well, the x value for this one is going to be right here, and the x value for this 5.01 is going to be right here. That's the question. Is what we're saying is, how close would we actually have to get to that value of 3 in order to make sure that our output is within 100th of a unit? Or you think you know? Well, that's pretty presumptuous. Let's see. We could just basically set up two basic equations here. We could say our output, which is 2x minus 1, when is that equal to our upper boundary of 5.01? And when is 2x minus 1 equal to our lower boundary of 4.99? And we could solve those, right? If we just add 1 to both sides, we get 2x is equal to 6.01. And we get 2x is equal to 5.99. What should I then do? I should divide both sides by 2. So x would be equal to 3.005. Or in this case, x would be equal to 2.995. So those are my x values right here. That's how close I have to get. 2.995 and 3.005. That will ensure that my outputs are going to be within 100th of a unit. So we're really zooming in on that area. Is everybody okay with how I got those numbers? Then the distance, as Andrew referred to, what is that distance? And what is this distance? 0.005, 0.005. So the width away, if we want to come within 100th of a unit of the limit, then our x values need to be within 5 thousandths. In order to move forward to the next step, you have to understand that if I want to be within 100th of the output, then my inputs have to be within 5 thousandths. Okay? All right. Here we go. Can you be sure that for all x values within that boundary, that all outputs remain within 0.01 of 5? Because we know it's a line, yes, we can be. But in some graphs, we have to ask this question. We have to say, not really. I mean, we got to within 100th of the output, and we would say that that's pretty close. Well, come on. I mean, if you're 100th off in terms of the weight of a diamond, that's a lot. You're going to be paying a lot of extra money, or you're not going to be getting your money's worth, one of the two. So 100th isn't necessarily a large, or isn't necessarily a small number. We could get infinitely small. In fact, we have to say this. Maybe the barcode thing happens. What if that happens within that, 5,000ths of a unit? And then I wrote this down. Maybe things get funky. Maybe there's just something weird that happens with that graph that we can't predict. Now we're working with a line, so that's pretty straightforward. We know what's going to happen. But what about all functions? What about all functions? So we come to the precise definition of the limit, and this will ensure that we know that we can prove that we are for sure approaching that number. You will have to memorize this perfectly for your next test. This will be one of the hardest parts for your test. The rest of this test is not very difficult. Here's the definition. Let f be a function defined over an open interval that contains a but might not be defined at A. That is the given premise. I'll let you write it down, then we'll draw what that means. So one thing I really liked about your test, you guys did a much better job in your test this year of explaining what happens with the slope of the tangent line and secant line than last year's class did. And I think that part of the difference is I encourage you to draw the picture first and describe what's happening. Well, the same thing is going to exist here. You need to be able to see the picture and describe what's happening. So what I have is I have some type of a function, okay, we'll call it f, and it's defined, meaning there's output values over an entire interval except possibly at the number a. So what I'm going to do is I'm going to put an empty spot at A. That doesn't have to be the case, but what we'll say for this part it is. So Curry, yesterday we talked about, local or relative, locally, an open interval. This doesn't have to be 5 units wide. This could be 100th of a unit wide for all we care. Okay, all right. So that'll help connect that for you. Then. So given this premise, the limit as x approaches a of f of x is equal to L. How would I draw that on the graph? As x gets close to a, what's this output? L. So I could put L on there. In most cases, we could just plug a into the function and it would give us L. But not all the time. Not in this case. This is the phrase that we want to define. This is our given. This is our premise which we drew. This is what we want to define. Here is the precise definition. The limit as x approaches a of f of x is equal to L if for every number epsilon greater than 0. Epsilon is going to be a really, really small number, and it's going to correspond with our outputs. If for every epsilon greater than 0, there is a number delta greater than 0, such that the absolute value of f of x minus L is less than epsilon whenever 0 is less than the absolute value of x minus a, which is less than delta. And that is it. This is going to take a little bit of time to digest. This you have to memorize. Trust me, this is the hardest part of your test. I think the median score on this test last year was 100%. The rest of the material we cover will not be that difficult. This is something that you have to chew on. And the reason why I want you to memorize it is if you saw it next year, I'd want it to be somewhat familiar in terms of the language. The good thing is we have already spelled out what most of this is. I'll give you another 30 seconds, try to finish it off, and then we'll actually mark this stuff down. We are out of here at 05. So, write this down. Epsilon. Epsilon is your outputs. So that's like how close we are to the output. Delta is how close we are to the inputs.